In our last lesson, we were interested in looking at counting the number of different ways a series of events could occur, or we looked at the number of possible outcomes when you had a series of events. What we're interested in today is how do we figure out how many different orders are possible for a number of things. So we've got a bunch of things, a set of things. We want to take some stuff from that set and we want to arrange it in a number of different ways. We want to see how many different ways we can order them, or we'll often use this term arrangement in place of that. Now, this lesson is called Permutations. This is also the title of this unit, Permutations. What we want to know is, what does this word permutation actually mean? And it turns out these two questions are actually asking the same thing. A permutation is just a way of figuring out how many different orders are possible for a number of things. So here we are, permutations. What is a permutation? It's an ordered arrangement of a set of objects. And again, this is straight out of your learning guide, page 1B1. Often these objects are selected from a larger set. So here's an example of doing a permutation using what's known as the box method. How many three-letter patterns can be made from all the letters of the alphabet with repetition? And what the with repetition means is that you can use the same letter over and over again. Letter over and over. So if the things that we have to arrange are all from the letter of the letters of the alphabet, we have 26 things to choose from. And if we're making a three-letter pattern, we set up these three boxes, one of them representing the first letter in our pattern, the second letter in our pattern, and the third letter in our pattern. Okay? And we ask ourselves, how many choices do we have for the things that we want to put in each box or in each place in our pattern? So for the first letter in our pattern, we have 26 letters of the alphabet to choose from, so we have 26 different possible things we can put in there. When we go to put in our second letter, we also have 26 choices to choose from, because we can use the same letter that we used in the first box. And in for the third space in our pattern here, again, we have another 26 choices. So the total number of choices is going to be 26 times 26 times 26, based on that fundamental counting principle that we talked about last time. So if we multiply this out, we get 17,576 different patterns we can make by choosing three letters. How many three-letter permutations are there from all the letters of the alphabet without repetition? So now, once we've used a letter once, we can no longer use it in one of our other boxes. So again, we've got three boxes because it's a three-letter pattern. We'll think about the first, the second, and the third letter in our pattern. We have 26 choices for our first box, but once we have placed a letter in this first box, or decided we're going to put a letter in the first position, we can no longer use that letter for the second box. So we only have 25 letters to choose from for our second position. And by the same reasoning, we only have 24 letters to choose from in the third positioning. So our total number of possible choices is going to be 26 times 25 times 24. And if we work this out, we get 15,600 possible choices. So we can do this using letters. We could do a similar kind of question using numbers here. Okay. How many four-digit arrangements can be formed using the numbers 1, 2, 3, 4, 5 without repetition? So again, it's a four-digit arrangement, so we're going to have four boxes representing the four digits in our number. And fundamental counting principle tells us we want to multiply the number of possibilities in each one. So we start usually in the first place. How many options it really doesn't matter where we start. But once we start in one place, it determines what we can do for the other boxes. So if we start here, we say, well, we've got 5 choices for that first position. We can use a 1, a 2, a 3, a 4, a 5. But once we've put one of those numbers into that position, we no longer have that number available for the other position, so we only have 4 numbers available, then 3, and then 2. So the total number of possibilities is going to be 5 times 4 times 3 times 2, or 120 possibilities. Now just be careful when you're doing these kinds of questions. We have formed an arrangement here, 5, 4, 3, 2. These numbers in these boxes don't necessarily represent one of the numbers, one of the 4-digit numbers that we have formed. They represent the number of possibilities for what numbers we can put in each of these places. Now there's an easier way of doing this kind of thing, or what we have just done right here is what is called a permutation. Okay? And some notation here, when we talk about a permutation, we'll often use this symbol here, P and then N comma R, or N, P, and then R. And what this permutation means is just what we've done up above. It represents the number of possible arrangements when some number of objects R are taken from a set of distinct objects with N objects in that set. So R is the number of boxes that we used up above. N is the number of choices that we have to place in the first box. So we can represent this question that we just did here as a permutation. It is the permutation of, we had 5 choices, 4 boxes. So P, 4, 5, 5, 4. Now, what we end up with when we do a permutation is we get this pattern of the first number times a number 1 smaller, then a number 1 smaller than that, and so on and so on. The general way of calculating this is, if we're calculating permutation and R, the first number, for the first box we have N choices, then we have 1 fewer choices for the next box, 1 fewer choices for the third box, and then so on and so on and so on. Should only have 3 dots there, all the way down to N minus R plus 1 for our final box. So we have 1 more than N minus R for the last choice. So let's do an example here. Calculate P, the permutation 11, 5 here. Well, if R is equal to 5, that means we are going to have basically 5 positions here, 5 things that we multiply by each other. We think of R as the number of boxes. So 1, 2, 3, 4, 5. What goes in the first position? That first number, 11. So 11 times 10 times 9 times 8 times 7. And then we can work out what this is, 55,440. Similarly, if we were to do something like this permutation, 6, 2, and we would have 2 boxes, 6, and then 5. So this would work out to be 30 here. So using this permutation notation can sometimes simplify the calculations that we're doing here. So just a slightly different kind of question, a variation on this forming digit sort of thing. How many 3-digit arrangements can be formed using the numbers 1, 2, 3, 4, 5 that are even and have no digits repeated? And the key difference between this question and the last one is that the numbers have to be even. So these 3-digit numbers that we form, or these 3-digit arrangements, have to represent an even number. So if we've got a 3-digit arrangement, we're going to have 3 boxes representing our 3 digits. Now, what determines whether a 3-digit number is even or odd? It's the number that goes in this final digit over here. If we put a 2 in here, or if we put a 4 in here, we will have an even number. Okay, that last digit is even, then our whole number is even. If we put a 1, a 3, or a 5 in that box, we will have our whole 3-digit number will be an odd number. Now, it doesn't matter what we put in the other two boxes. If we put a 2 or a 4 in that final box, no matter what goes in the first two places, it's going to be an even number. So we have two choices for what goes in that last box if we want this to be an even number. Now, how many choices do we have now for this first box over here? If we've already picked something that goes in this box, we only have 4 numbers left to choose from. And if we've put one in the last box and one in the first box, now we only have 3 possibilities for this box right here. So the total number of possibilities here is 4 times 3 times 2 is 24.